Quantum Foam, Episode 25. Time and Infinity.
Physics. Physics is at the foundation of all the mathematical principles that guide the heavens. You have to understand physics.
More than likely, that's not going to happen, but
Forces which govern the universe. Physics.
to infinity and beyond. Boltzmann and beyond. Boltzmann. I gotta figure out what this says. I cannot read it. I all of a sudden went to code, and I cannot read it. Hold on, let me decode it. Boltzmann. Infinitely many things. Time and infinity. Boltzmann. So this is something that is a known idea. Infinity. Beyond infinity. One way to begin looking at this is taking some rational thinking. So let's expand our number system, introduce all negative numbers. This forms a set of what is called integers. Obviously, it won't help us reach a larger cardinality. We've doubled this set by adding the negative numbers, but it's still nowhere near infinity. We get this idea of what it is, but there's just a few things we need to know about it. The current modern thinking comes from this guy, Cantor. He showed that you can include all the numbers, including the ones written as fractions, of a set of rational numbers. Kind of hard, but not impossible. Think about things a little differently. The key is to realize that in order to pair off the rational numbers with natural numbers, we just need to find a way to list the rational numbers in some sort of order, some sort of index so that we can keep track of it. Seems good, but we got to dig deeper into this. So there's no such thing as the smallest fraction bigger than 0. You can't divide by 0. There are lots of doubles. 1/2 is the same as 2/4. So we can't have 0 in the denominator. And the problem is being able to write them a million different ways. So we can describe these as the real numbers. This Cantor supposedly could prove that it was impossible to create a bijection between the set of real numbers and the set of natural numbers. No matter how hard you try, you'll always end up using all of the natural numbers and still having real numbers left over that aren't paired with the natural numbers. What they're saying is there are more real numbers than natural numbers. But remember, there was the proof from 2009. We mentioned this. P is equal to T. The infinity surrounding P is equal to the infinity surrounding T. Not P is greater than T or T is less than P. In that case, the natural numbers is less than real numbers. So one of these is a philosophical standpoint using math, and another is another mathematical standpoint. It could be described as that. And you can't have proof by contradiction. You can't have beginning assumptions either. His argument is sound, but not solid, so to speak. And believe it or not, the way you think of things, some infinities are greater than others. These are some of the problems we had in even trying to conceive of the problem of infinity. The moral of this story is that we may not be able to travel infinity miles an hour, but you could argue that math allows us to explore infinity and beyond. So, different infinite sets can have different cardinalities. Some are larger than others and may seem esoteric, but the understanding of infinity and set theory, group theory, and stuff that's related to it, string theory even, it's vital to understanding the very foundations of mathematics and the foundations of reality. It took a long time to come up with even what we got now. Keep that in mind. There are some other things here too. We are interested in infinity as it relates with time. Time and infinity, the essence of both. Does time have infinite span? Was there a beginning and an end? It seems like time had a beginning and probably an end by its nature. Yet, we're treating time like a variable in these equations, the same as though they were spatial dimensions or math structures containing subsets of spatial dimensions. 9 extra dimensions instead of 3.
Easy now. String theory still means a lot.
What? What kind of bullshit is that?
You know it's true.
Sounds like a quantum mechanical function that is having its wave collapse. That's what it sounds like to me. It's fallen through. Bullshit. Boltzmann. Fucking Boltzmann. According to Bolzmann, after the beginning of the universe, it takes a while for time to find its direction. So how do we know that time is going forward? Okay, well, we're labeling what we see as forward. So what we're saying is we're describing the direction it took. So some of these concepts, decoherence, that was introduced by German physicist H. Dieter Zeh in 1970. Big topic in the 1980s, obviously. A particle frenzy back then. We'll be getting into the Standard Model. We'll mention some of the more well-known particles. And it comes down to what, according to Michio Kaku, he had to learn 1,000 particles to get his PhD. We don't got to do that. I don't care what star system you're from. You don't need to learn all these theoretical particles. But we will mention some of them so that you know what these people were working on for dozens and dozens and dozens of years. There are certain things about time and infinity. We, over a dozen episodes ago, went over a time problem. There's a problem with time that we have been able to surpass due to being in states of dissociation. And that only allows looking cyclically. It gives the ability to look completely objectively at your situation. We were able to think of time and infinity in a slightly different way, possibly in a way that can get past these issues with infinities. Now, it seems to me there was an entire science festival or something. They had a couple physicists on there, some leading group theory people, and this was in 14. Were they unaware of the PT infinity proofs from 09? Or were they unrelated? Seems to me that that's related. But of course they didn't mention that in their stuff. They got their moment to shine at that little thing. But they did go into some good stuff, something that I wanted to mention here a little bit later on. So there are interesting things with time. If you can just create your own embolisms, September 3rd through September 13th, 1752 doesn't exist. If you ever see a date written in that time, it is false. According to our calendar, September 3rd, 4th, 5th, 6th, 7th, 8th, 9th, 10th, 11th, 12th, 13th doesn't exist. Look at the calendar. 1752. We went over some stuff with leap day on leap day. Before, I wanted to throw that in there because it relates to being able to get past your time problem, which we have figured out a way to do. One example of that is writing your dates how you need to, keeping track of time relatively for each aspect of your study. So there is no master time. There's only instantaneous time.
I beg to differ.
Why is this important? Why is all this important? We are looking at things like the loss of information into a system.
We were unaware of those phenomena at the time.
Black holes, antiparticle and particle being ripped apart from one another. Half of them being spatially closer to the event horizon, the other half just beyond the horizon spatially. Quarks being ripped apart, antiquarks being ripped apart, positron electrons being ripped apart. So, is this a loss of information? Well, according to Hawking, Bekenstein, Susskind, all of these guys, you can only divide the surface area of the black hole so many times down to the Planck length. And at the Planck length, the surface area is filled with little dots of Planck length particles that can be described using math. The surface area is directly related to the amount of information in the black hole, and so, according to these guys, there is no information loss. There is something emitting outward from the black hole, but it isn't in the black hole, it's from the event horizon surrounding the black hole. So it appears as though it's the black hole. Hawking radiation.
What you are talking about is the holographic principle. This prevents the loss of information by projecting all the same 3D information on the 2D surface of the black hole, which is really just a vantage point of the black hole from the observer in question.
The surface area is where the information lives on the black hole. What is important about this loss of information or not is it directly deals with infinity or not. Infinity or finite. And remember geometrically what a singularity looks like. Infinity or not is a top-looking structure, three-dimensional circle, horizontal with a screen. So let's take a look at the 3D grid box from a top corner vantage point. You can see down into the circle. It gets smaller and smaller and smaller all the way down to a point. Singularity. Looks kind of like a tornado. The problem here is it has a infinite surface area, but it has a finite volume. According to what we can do with calculus, we can calculate the volume of this shape, but we cannot calculate the surface area. Well, what? It's one shape. If it's a shape that goes on forever, how can we calculate the volume? How do we know that that infinity is just smaller than another infinity? What's really happening here is that circle to dot figure. It's a 1D to 2D technology. It's one dimension to two dimension technology. It's blue to green technology. It's white to black technology. It's technology. So somehow all of this ties into loss of information into the system. It's technology. It still doesn't solve our measurement problem. It's technology, which we affect the measurement by measuring it, sharing quantum information with its surrounding. The reason why we're doing everything we're doing here is for the purpose of quantum computing. We need an undisturbed evolution of quantum coherences.
That was what my communication question is about. I'll wait for now, though.
So what is this really all saying? We're worried about time here and how infinity deals with that. Infinity itself is a subject, but the infinities of time. When you look at this in terms of quantum mechanics, this is where you have your collapse of your wave function, which essentially means it's an event in quantum mechanics that means certain things. So logically speaking, dealing with this time stuff, this means that time goes in the direction of the lost information. That is the direction time goes. It goes towards that chaos. This stuff heavily deals with Yang-Mills theories, string theory stuff, things that describe particles in the standard model. The gauge principle, where there's gauge invariant curvature. It's a fucking wormhole. It's mathematical alchemy. The inhomogeneity, free geodesic equations, partial elucidation. There is no evidence that there are these fibers, these fiber bundles in gauge theories, in the gauge principle. It's mathematical alchemy. It's like the gauge of a wire, made up of little wires of each dimension. There's no evidence. It's from 86. There's no evidence. So these are dealing with Dirac operators. There's no evidence. The isotopic spin of your particles. This is the genesis of the equivalence principle. We have problems with things like spontaneous symmetry breaking, gauge fields, quantum corrections. These are some of the problems we have that we can't quite explain yet. Spontaneous symmetry breaking, why do we have symmetry sometimes and then not other times? We break apart an electron and quarks pop out. One of them spinning this way, one of them spinning that way. At what point do they stop having asymmetry? This is the point where it is what they call spontaneous symmetry breaking. We can get into condensed matter physics or having the power to alter states that have the ability to change. Also high energy particle physics. How all this deals with infinity when you are dealing with curved space and the like. Essentially, you're describing a graph where particles at certain points have infinite degrees of freedom. So you are dealing with infinities within your curvature. And so they need to be done accordingly. And if you don't have the correct technique to use to solve, you're going to be shit out of luck. We know how to solve the volume of the light cone that is a singularity. We don't know how to solve for the surface area. But according to some scientists, Max Planck himself was a very conservative scientist by nature, and he hated doing things like exactly what he did. In order for us to come up with a quantum mechanics method, you have to look at energy in discrete packets. There's no other way to do it. Frequency number. He put the discrete packet amount equal to the frequency of the radiation laser. These infinities and this time. Infinity is denoted by a lemniscate. That's what it's called when it draws it on the calculator. Little 2D thing looks like an 8 sideways. Lemniscate. Sideways 8. This symbol was first used in the 17th century. Somebody wrote something up on conic sections. Obviously, there's some infinities to deal with there. A conic section is where planes intersect a cone. And remember, a light cone would be a cone where one of the dimensions has a curvature to it. This infinity symbol started appearing on tarot cards. It's starting to be a thing. So we're looking at infinity, and this goes all the way to the big and all the way to the small. We're worried about whether or not we can infinitely divide between 1 and 2, or if we can count upwards, 1, 2, 3, 4, 5, on upward infinitely. So we have to stop at a certain size, this Planck length, when dealing with the surface area of a black hole, and just take that as your grid. Planck length. Planck length. Obviously, this is the midpoint of episode 25, Time and Infinity of Quantum Foam. Quantum foam. Planck length. Planck. Take that as your static grid that you can do perturbation theory on and figure out what's going on. And even though I understand and trust Bekenstein and Hawking, we still need to take a look at them. I said we were taking a look at everything and questioning everything, so that is what we're going to do.
I'm okay with it.
So this George Cantor, we mentioned him a little earlier, in the late 1800s, he finally created a theory of the infinite, which was consistent. Of course, it demolished the Aristotelian scholastic proofs that no such theory could be found. Obviously, it could. His point had to do with the uniqueness of the representation of a function as a trigonometric series. So, mathematician Benoit Mandelbrot, fractals. This idea of infinite, these fractals, you've all seen it. Fractals. It starts to look like a snow globe. You start that out by adding a little edge to a line, adding a little triangle to a line. Then you add a triangle in between that, and then in between that, and then in between that, so on and so forth. These are ideas of infinite, absolute infinite, physical infinities, mathematical infinities, and the relationships thereof. We got temporal infinities. This is where we were looking at our light cone. Now, let's draw one of the Big Bang. We are treating time as existing not before the Big Bang. There are descriptions of the world as an oscillating system. It essentially looks like a bunch of strung up Tootsie Pops. A circle, and then a point where it connects. A circle, and then a point where it connects, and so on. What we're trying to do is figure out why the way things are seem to want to avoid infinite time in an endlessly oscillating universe. This is sort of what you could call the eternal return. There is eternal recurrence from geometry, relativity, and the fourth dimension. B. Rucker. R. B. Rucker. Let's see here. What other kind of infinities are there? There's spatial infinities, infinities in the small. All this time has been spent over the last half century at the LHC using particle accelerators like the LHC. They discover there's lots of different elementary particles. Here's the thing. I am unsure as to whether or not they got it right as far as do you just create particles infinitely many times, and we've only done what we've done, so we've created what we've created. And I have a feeling that there's an issue that goes back pretty far. And this issue goes back to relativity, directly challenging Einstein.
I deduced as much, but go on.
Here's the thing. I think as far as what Einstein spoke about, he got it right. For a brief approach at a theory of gravity, Newton got it right. For orbits, Kepler got it right. For the speed of light, Galileo got it close to right. For heliocentric, Copernicus got it right. A lot of people got it right. They're like, why do we live on a globe? We don't know. Who knows how big? Who knows such things? Some people wanted to really know. So that is some interesting revelations that are from what they have been finding out in the particle accelerators. Who knows such things? The ideas of infinity within the mind as well. How do you regard an infinity that you create within your mind as a mental device talking about infinity? Are you even able to do that? Well, obviously, yes. There are various objections to this sort of mental or physical intangential infinity. It's like Descartes and the infinite representations of wax. Can't we theorize and pronounce that an infinite arrangement of wax can be done? Can we all agree about this? We can. That's the mental construct thing. Aristotle, Aristotelian. One is the Aristotelian argument that unless one is actually smashing the stone down, actually hitting the particles and breaking them apart, you could throw a stone at a particle and break it in half, but no one will ever carry out infinitely many divisions at some point. So there's really not infinite numbers of particles. There are objections to this. They're pretty sure of what they've detected. We're looking at annihilation energies, muons. The question of whether or not matter is infinitely divisible might not ever be known, but there are various conjectures that may not even matter for solving this theory of everything. Oh, what's the answer to this question? Who knows? But that's not the answer we're looking for currently. Cool story, but I don't know if that's going to pass. We don't know whether or not infinity lasts forever. Who cares? We are also interested in time and infinity, infinite time. So we are interested in certain aspects of infinity. There's just certain concepts you got to understand, like infinity and infinity squared. It's still infinity. People like to compare things like there are certain scales. You can keep track of the scales of everything. The universe is on the order of this. Galaxies are on the order of that. Suns and planets are on the order of this. Bacteria is on the order of this. Fundamental particles is on the order of that. Quantum foam is on the order of it all. The intricacies of these infinities may not be necessarily important. And we have to make sure that when we're doing multiple things that are really the same thing, they have to be reduced down for brevity purposes so we can understand what's what. 2/4 is the same as 1/2, and a bunch of other things. Everything has to be looked at in the correct way. That is the big problem.
Well, you are the problem solver here.
Apparently there is a Quanta Magazine podcast, and I'll be looking into that very soon, I'm sure. Quanta Magazine's science podcast. So I was looking up this article. I'm glad that it's Sabine Holzenfelder, somebody who's actually reputable and knows what they're talking about. I spoke a little bit about her in the loop quantum gravity episode. So they say string theory meets loop quantum gravity. Two leading candidates for this theory of everything. Now, how does this relate to infinity and time? How do we enter that into this stuff? Well, let's take a look at this. So the supposed eternal return of infinity. We mentioned this a little bit ago. The idea of eternal return is that every so often the universe repeats itself. We see various patterns indicative of oscillations of some kind. This is why we theorize when we describe light cones as an oscillating system. This describes a world that repeatedly goes through oscillations, expansions, contractions, and the like. That idea is going for infinite time. We may not care ever if we can find out if infinity is a real thing, if infinity is just a concept, or if space and time really is infinite or not. They look at all this stuff by manifolds, infinite and unbounded, or finite and bounded. So there's infinite and unbounded, then there's finite and bounded, then there's finite and unbounded. So finite unbounded could be looked at like a loop. Finite bounded could be looked at like dot, line, dot. Infinite and unbounded could be looked at like arrow that way, arrow that way. We're really more interested in how this relates to time than it does infinity. We all know how to deal with infinities. This just comes down to the minuscule mechanics behind these theories. 6D space, 5D space, 4D space. If these are all just theories, then why not have a theory of the minimal possible amount of dimensions? How about as many dimensions as we actually see? That's a good one. As this infinity deals with the small or the big, we think we may have figured out the indivisible problem. That's a good one. Looking at these annihilation energies again, that's a good one. The question of whether or not matter is infinitely divisible, that may not matter. We know that. This is how we get from 1D to 2D, 2D to 3D, 3D to 4D. So this mountain, stone, speck of dust, objects on the earth, if they occupy space, the continuum, then we can think of what level we see this as just being somewhere in the middle of the picture by looking at it. This is the perceptual level. This example gives you the biggest thing in a picture, the middle thing in a picture, and the smallest thing in a picture. Where do you start counting objects as an object? Was it Brian Greene that explained the analogy where you have a fly in the room and then you're in a little 12 by 12 room or something, you have a fly. It might be flying 2-3 meters a second. How far away is it from you? Is there a radius? Is there a point in between the distance between you and the fly? And when it's going 3 meters a second, 30 meters a second, etc., how many points of space is between? So that is some of the things that loop quantum gravity attempts to answer, because it is approaching the problem from a background independent curvature, warpature of space-time as its fundamental premise. Space-time is a bunch of little quantum regions that connect together and cohere together to make our macro world the size of particles that we can see. And once again, that does not get past the measurement problem. When we have a way to do that, we will let you know. I will let you know. That does not get past the measurement problem. We breached upon a priori. I will let you know. Infinity is the epitome of the unknown. And so as this relates to time, that's what we're worried about here. The reason why we're able to manipulate these functions and do this math and physics is because we can alter the time. This is the only way that we're able to conceive of these concepts. We have to break them down this way. That is the only reason why we are treating time any differently than another dimension. It does have a direction. Each dimension may have a set of dimensions to describe that dimension, because some of these are folded over because that's the way dimensions work. 4 dimensions goes into a realm that's outside of a 3D space. The best way to visualize this is to say a circle is a 2D shadow of a sphere, a ball, and a box wireframe lattice. The shadow of that, when you shine a light, the shadow of that on the wall, that is the best approximation of a tesseract. You can sort of see it. We could just be the shadow projection of 4D onto 3D. You can look at it like that. We probably are that. There is not a single coherent theory for that either. Who is a Platonist and who is not? That don't matter. Galileo's paradox. An infinite set can be put into a one-to-one correspondence with a proper subset of itself. That is what we're doing here. You're counting 100 things, then you're having a separate area that says, I have 100 things that I counted. That's all it is. A certain subset of itself. Had we assumed in advance that no set could be put into a one-to-one correspondence with a proper subset of itself, then we would have had a proof before that no infinite set can exist. These are unwarranted assumptions. That is what we want to try to prevent. Of course, another famous curious proof by Kurt Gödel in 1930. The consistency of set theory cannot be finitely proved. This proof proves that this theory is unknowable. But you're not really saying anything. You're saying half of almost something, which still is nothing. Remember, if you only know one of the fundamental forces and the physics surrounding such, you can't fill in the blanks for the other 3. You need to know all the other 3. And even with the unknown, you could look at the measurement problem as quantum mechanics unknown that you'll never know and compartmentalize it down to a quarter size of the whole. I've alluded to this previously. Infinity. Kind of infinity, sort of infinity, absolute infinity. What is actual absolute infinity? How does it relate to our time? Is infinite time something that we can count on? Because for various reasons and justifications, you can say that the existence of an actual infinite is impossible, because you have to count infinity. We're trying to count to infinity, but who is going to do the counting? Then when it's all said and done, they say, this is how long it took to count to infinity. And they're still going. And then there's the time after when they declare such thing. There's time there too, isn't there? So this is the conundrum. Thomas Aquinas, George Cantor, Bernard Bolzano's paradox of the infinite, Cantor's absolute. These are just some bigwigs dealing with this infinite. It goes into the philosophy. So how do you go deep into the philosophy of physics? What? The physics of philosophy or the philosophy of physics? Well, the philosophy of physics is what I'm talking about here. The deeper issues, the bigger, deeper issues. That is what we're aiming to do in this podcast. We do have some time to jack around here and there. All right, Mr. Rucker, I'd say it's a pretty sound start. We can get into even bigger issues of religious mysteries and points of faith. What's surprising is the fact that it's not surprising, but we're not going to get that far into it. We just need to be able to deal with our infinities.
I'd say we are much better up to speed.
And we're able to do that. We have a method to deal with our time problem.
Word up. Mr. Physics Gangsta.
That's really just for shits and giggles. But what it is being able to really objectively see the big picture or not. Oh, you think you do, but you don't? You might be wrong. Question everything down to its core and then build stacks upon stacks upon stacks to make sure that there are no kinks in your chain of your material that is your understanding of time and infinity.
To infinity and beyond.
To infinity and beyond.
To infinity and beyond.
Okay.
Now we are getting somewhere with these episodes.
Wrap some of this other stuff up. This is it for episode 25, Time and Infinity of Quantum Foam.
The zeroth wave disclaimer.
The views and opinions expressed in this podcast are those of the author or authors and do not necessarily reflect the particular views, thoughts, or opinions of Zeroth Wave Productions, any of its sister companies, its parent company, Zeroth Enterprises, or any other entity which had existed, will exist, or which, quote-unquote, presently must exist outside the realm of our current space-time.
Quantum Foam is produced by Zeroth Wave Productions.